Michael, what's today's audio topic?
Today's about ordering the SMSL clock generator G1.
So you ordered the clock generator you'd been considering. By the way, what exactly does a clock generator do again?
Let me explain, including the role of a clock generator.
Master wants to hear about the clock generator too, right?
Yes, I want to hear.
I've talked about the role of clock generators before, but let me briefly explain again. A clock generator is a device that establishes the reference timing for digital signal processing. The accuracy of the clock generator is crucial for reducing the effects of jitter. In digital audio, the clock synchronizes the timing for sampling analog waveforms and transferring data. Playback devices extract signals at regular intervals according to the clock and perform DA conversion. While DA converters have built-in clocks, a clock generator is a device that produces a more accurate clock signal than that.
Michael, you plan to use a clock generator with the SMSL D200 you bought last time, right? Isn't the built-in clock in the D200 already excellent?
I don't know. The reason is I've never used a clock generator before, so I can't compare it to the D200's built-in clock. I decided to introduce a clock generator because it might improve the sound.
Michael, you're really inquisitive.
Because audio is my hobby. Now, let's talk about the SMSL G1. The G1 generates a 10 MHz clock signal. It can output to up to 4 devices total.
There are people who own as many as 4 digital devices.
If you have a CD player, DAC, network streamer, etc., the number of devices increases. Having more devices makes synchronization meaningful, so having more clock outputs is advantageous.
Why does a clock generator produce a 10 MHz signal in the first place? CDs are 44.1 kHz, right? It seems completely unrelated to 10 MHz.
Good question. Let me explain why clock generators produce a 10 MHz signal. In the audio world, a 10 MHz clock and a 44.1 kHz sampling frequency seem completely unrelated at first glance. In reality, 10 MHz is merely the reference frequency, and the 44.1 kHz clock is derived from it.
Is that accurate? I get that 10 MHz is much finer than 44.1 kHz, but they're not divisible numbers.
John's questions are sharper than usual today.
I'm blushing.
Inside audio equipment, sampling clocks like 44.1 kHz, 48 kHz, and 96 kHz are used. External clock generators don't directly produce those frequencies. Instead, they send 10 MHz as a master reference to the device. Inside the device, a PLL, phase-locked loop, then generates clocks like 44.1 kHz.
PLL?
A PLL is an electronic circuit that can accurately generate any frequency based on a 10 MHz reference. For example, using the externally supplied 10 MHz as a reference, the DAC internally generates 22.5792 MHz. The 22.5792 MHz frequency is then further divided to obtain the 44.1 kHz sampling signal. In other words, the 10 MHz signal doesn't directly become the audio sampling clock. Instead, it serves as an ultra-high precision reference, master clock, fed into the PLL's reference input.
So, since there are various sampling frequencies for audio, the first step is to generate a high-precision 10 MHz clock?
Exactly. The reason 10 MHz is widely used in audio is because it was originally the standard frequency for measurement and communication equipment. Furthermore, 10 MHz is easily convertible to 5 MHz, 2.5 MHz, 1 MHz, etc., as it's easily divisible and multiplicable by integer factors. Therefore, OCXOs, oven-controlled crystal oscillators, and Rubidium oscillators are often designed based on a 10 MHz standard. In other words, 10 MHz spread as a common standard in precision instrumentation, not just for audio, and audio manufacturers adopted it for their own use.
That's quite an interesting story.
Let's get back to explaining the G1. The G1 uses an OCXO to generate its clock. It houses a dual thermostatically controlled OCXO in an isolated chamber, maintaining stable temperature to guarantee clock frequency accuracy below 3 ppb.
What's an OCXO?
An OCXO is a type of oscillator. It's a term that comes up when discussing clock accuracy. There are three main oscillator types: crystal oscillators, OCXOs, and rubidium oscillators. Let's outline their mechanisms, characteristics, audio benefits, and considerations. 1.ST crystal oscillator, XO. Crystal oscillators use the piezoelectric effect to generate a stable frequency. It's the most common clock source used in nearly all digital devices like computers, smartphones, and DACs. Crystal oscillators are inexpensive, compact, and consume little power. However, they are susceptible to ambient temperature and power supply noise, resulting in less than ideal frequency stability. Entry-level to mid-range DACs often use crystal oscillators. While crystal oscillators can produce sufficiently good sound, they are considered to have limitations in spatial expression and sound imaging compared to high-end solutions. Second, oven-controlled crystal oscillator, OCXO. An OCXO is a crystal oscillator where the crystal is housed in a small oven and maintained at a constant temperature to enhance frequency stability. This significantly suppresses frequency drift caused by temperature changes. The defining characteristic of an OCXO is its extremely high frequency stability, around ±0.01 ppm. It also offers excellent jitter characteristics and high temporal precision. However, it requires a warm-up period of several minutes to over 10 minutes and is relatively expensive. OCXOs are commonly used in high-end DACs and external master clock devices. Regarding sound quality, it is said to provide a more solid core, clearer localization, and improved spatial representation.
So the G1 uses an OCXO too? Does the G1 have a warm-up time?
Only when using AC power does the LED flash for about the first 2 minutes until the OCXO's temperature stabilizes, making it unusable during that time. But since the G1 lacks a power switch, the power stays on unless you unplug the cable. Therefore, the warm-up period only occurs once, when you first plug in the power cable. Third, rubidium oscillator. A rubidium oscillator is a device that synchronizes the oscillation frequency of a crystal oscillator to the natural frequency of rubidium atoms, generating an extremely stable frequency. The characteristic of a rubidium oscillator is its very high long-term stability at the plus or minus 0.0001 ppm level over years. Because its frequency remains virtually unchanged over time, it is used in applications like broadcast stations, communication satellites, and GPS. However, its short-term jitter characteristics are not necessarily superior to those of an OCXO. It is expensive, large, generates significant heat, and is often excessive for general audio equipment. Rubidium oscillators are used in some high-end audio systems.
So you're saying a rubidium oscillator isn't necessary for an audio clock generator?
If cost isn't an issue, a rubidium oscillator might be fine, but many argue an OCXO is sufficient.
I see. Michael went with the G1 using an OCXO.
A clock generator using a rubidium oscillator costs over $6,000. Besides, the G1 is advertised with an accuracy of plus or minus 3 ppb, which is more than sufficient performance.
Plus or minus 3 ppb? Not plus or minus 3 ppm?
ppb is 1,000th of ppm. The G1 clock's accuracy is extremely precise.
If the clock is that precise, the DAC signal should be accurate too, right?
That's exactly why I ordered the G1.
Well, let me know how it goes when the G1 arrives. Master, today's discussion about clock generators was interesting, wasn't it?
Yes, interesting.